Hello everyone, this is the presentation of the paper Compressing Geodesic Information for Fast Point-to-Point Geodesic Distance Queries, which is joint work by Craig Goldsman from the New Jersey Institute of Technology and myself. I'm Kai Hohmann from the Università della Svizzera Italiana in Lugano. The geodesic distance between 2 points on the surface is the length of the shortest path connecting them, and several very sophisticated algorithms exist to compute these distances. On the one hand, there are algorithms that find the exact distance, including the seminal methods by Mitchell, Mount and Papadimitriou, and by Chen and Han, and the fastest exact algorithm to date is probably the vertex-oriented triangle propagation by Qin et al. On the other hand, several algorithms have been developed for approximating geodesic distances. The pioneering work by Kimmel and Sethian adapts the fast marching method to work with triangle meshes, and another approach that is also based on discretizing and solving a certain PDE is the heat method from 2013. In the same year, an algorithm based on the saddle vertex graph was published, which follows the idea of adding edges to the edge graph of the mesh, such that distances can then be determined by finding shortest paths in this augmented graph. The discrete geodesic graph method uses a similar strategy, and its subsequent improvement, FastDGG, is probably the most efficient approximate method to date. Just like the fast marching and the heat method, DGG can compute a whole geodesic distance field from one source vertex to all other vertices of the mesh in linear time. But this runtime does not improve if only the distance between a pair of points is needed. In general, all these and other methods are too slow for interactive applications that rely on rapid answers to random point-to-point queries. One possible solution is to compress and store the geodesic distance information in some way in a preprocessing step and to use this database to speed up the online queries. A trivial solution would be to just compute and store all pairwise distances. But while this allows for instant queries, it would require a prohibitively large database, for example 100 megabyte for a mesh with just 5,000 vertices and 1 terabyte for a mesh with 500,000 vertices. In this presentation, I will not tell you about a new way to compute geodesic distances, but rather explain a novel divide and conquer strategy for compressing geodesic distance information, which can rapidly determine the geodesic distance between any two vertices on the fly in logarithmic time using a moderately sized database that is generated in a preprocessing step. Our method can be used to compress and recover exact as well as approximate distances using any existing geodesic distance algorithm as a black box, and we tested it with several state-of-the-art methods. The key insight that we use in our method is the following novel view on computing geodesic distances. Suppose you have a surface M that is split by a curve C into two parts, and you have 2 points in either parts of the surface. Now, by the triangle inequality, we know that the geodesic distance between x and y is less than or equal to the sum of the geodesic distances from x to z and from y to z for any z on the curve C. And we also know that this triangle inequality turns into an equality for some point z on the curve, and that is exactly the point where the shortest path from x to y straddles the curve C. Now that means we can compute the geodesic distance from x to y by solving a minimization problem, where we minimize the sum of the distances from x to z and from y to z for all z on the curve C. And this works as long as x and y are separated by the curve C. Now to make this work on general surfaces, we need to guarantee that x and y are always separated by some separator curve. And to get there, we first compute a nested bisection of a given surface with balanced separators. For the torus here, it means we first cut the torus into 2 halves, for example, along these 2 loops, and then we keep subdividing these parts in a nested fashion to arrive at small leaf patches. For example, the left half of the torus, we can cut it along this loop into 2 parts like this, and the right part of the torus, we can also cut it like a bagel into 2 halves like this, using 2 separator curves that are not a loop. So once we have this, we have basically a binary bisection tree T, and each node of this tree T represents, first of all, a surface patch, that is some subpatch that we have generated in this process of the original surface, and apart from the leaf nodes, it also represents a separator that consists of 1 or more separator curves. And once we have built this separator tree T, we can associate with any point x on the surface first a leaf node and a corresponding leaf patch that contains the point x, Second, a path gamma x from the root of t to this leaf node nx. And third, all the separator curves on the way. That means all the curves C that are represented by the nodes n of the path gamma x from the root node to the leaf node. Another example for this point y that lies on the other part of this torus, it would be this leaf node n6, because that's the patch that contains y, and the path gamma y would be the one from n1 to n3 to n6, and all the separator curves, these four that are associated with the nodes n1 and 3, are now associated with the point y. Now, given this information, we can now guarantee that any points x and y are always separated by some separator curve. More precisely, they're separated by some separator curve that is associated with the least common ancestor of the leaf nodes nx and ny. In this example, it would be the root node n1 itself, and indeed, in the root node we have a separator consisting of two separator curves, and together they separate x and y. And any path from x and y is deemed to straddle either the curve C11 or the curve C12. So if we go back to the optimization problem, we can solve this optimization problem where we find geodesic distances as the minimum of the sums of geodesic distances from x to z and from y to z. If we solve this for all z in the curve C11, we get the length of this shortest path. And if we do it for all points z on the separator curve C12, we get the length of the shortest path over here. And of course, the shortest of the two is indeed the geodesic distance between x and z. So here's another example. If the points x and y are like this, then the least common ancestor of the leaf nodes n4 and n5 is the node n2. And if we look at this corresponding separator, that's the curve C2 here, and the shortest path from x to y that runs through C2, if we measure its length and determine it by our optimization problem, then indeed we get the globally shortest path from x to y. And this works, except if x and y are in the same leaf patch, then of course the least common ancestor is just the leaf node itself. We cannot apply this method because they're not separated, but usually our leaf patches are so small that in this case we simply can approximate the distance by just the Euclidean distance, and we found that this works quite well. There's just one caveat. So if our surface has holes, like this one, it may happen that this method doesn't work. So for example, if we separate this surface first by this separator curve into parts P2 and P3, and then patch P3 into these patches P4 and P5, and now have a point X in P4 and Y in P5, then the least common ancestor node of the leaf patches is, in this case, N3. And if we look at the length of the shortest path through the corresponding separator, then it's the length of this yellow path, and that is not the globally shortest path between x and y. It's only a locally shortest path, because distances are only computed within the current patch, so here within the patch P3. Now, a solution to this problem is to simply examine all separator curves that are associated with both nodes x and y, with both vertices x and y. Because if we do this in this example, you can see that we also examine all the separator curves belonging to the root node at n1. That's also on the path from n4 to the root and from n5 to the root. And then if we solve the optimization problem for the corresponding separator curve, then we indeed find the length of the globally shortest path. So taking then again the minimum of all these paths that we have found, we find the shortest geodesic distance. So the only change to what we said before is to not only examine the separator curves belonging to the least common ancestor node, but to do it for all separator curves that are associated with both points x and y. And in the paper we prove that this method is guaranteed to always give the globally shortest geodesic distance between 2 points. Now we've talked a lot about these distances to separator curves, and that's of course not just a single distance from x to a point on C, but it's the distance to all points on the separator curve. Now to model this, we parameterize C by arc length, and then we can represent all these distances as a function of the arc length parameter t. Now these functions sometimes can be quite complex, and in order to store them, we approximate them by a low-degree polynomial. So here you can see an approximation with a quadratic polynomial, here with a quartic and a sextic and a degree 8 polynomial, and you see that, of course, the error goes down as we increase the degree. And we found that degree 12 is in most cases more than enough to get down to a very reasonably small maximum approximation error. And the advantage of this is that now we do not have to store all the distances to all points. That would be a continuum of values, but all we have to store is just the coefficients of this approximating polynomial. And that captures all the distances from a certain point x to all the points on the separator curve. Now we have all the ingredients ready to build the database. So we first take our given surface and build the nested bisection tree. And then for every vertex on the surface, we store the index of the leaf patch that contains the node, in this case 4, the indices of all associated separator curves, in this case 2, 1, 1, and 1, 2, and the coefficients of the corresponding distance polynomials. And this, of course, creates then an overall database of size O of n log n, where log n comes from the height of the bisection tree, so that is related to the number of associated curves. The m is the number of coefficients in the approximating polynomials, and n because we have to do it for every vertex. So now let's see how we can use this database to answer distance queries on the fly. In this example, the surface is first split by C1 into a left and the right part. The right part is split by C2, the left part by C3, and the bottom right part again by C4. Now suppose we have a point X in the leaf patch P4 and a point Y in the leaf patch P9, then the corresponding database entries will look like this. We have the leaf patch indices for both points, we have all the associated separator curve indices, and all the coefficients of the approximating distance polynomials. To compute now the distance between X and Y, we first check the leaf patch indices. If they are the same, then we know X and Y are in the same leaf patch and are not separated by any separator curve, so the best we can do is to approximate the geodesic distance between them by their Euclidean distance. Since the leaf patches are usually very small and almost flat, this is a rather good approximation. Otherwise, we resort to our optimization method. So for all the indices of separator curves that X and Y have in common, in this case 1 and 2, we consider the separator curves, in this case C1 and C2, and for each of them, we minimize the sum of the distance polynomials that approximate the distance from X to this curve and from Y to this curve. That means we find the parameter t for which this sum polynomial, which is again a polynomial of degree m, is minimal. Now this can be done, for example, with Newton's method, and a small number of steps is usually sufficient to get to the minimum, so we can assume that number of steps to be constant, but the evaluation of the polynomial itself is of course O of m, so this we assume can be done in O of m time. But we have to do it for all the separator curves that X and Y are associated with, and in this case, so we first do it for the separator curve C1, finding the length of the shortest path from X to Y straddling C1, and then we do it for C2, finding the length of this shortest path. Now the minimum of these two lengths is then the geodesic distance between X and Y, as we have shown before. So in the worst case, this algorithm runs in m log n time, where m is a constant, the maximum degree of polynomials we use for the approximation, and log n is again the height of the bisection tree, which corresponds to the maximum number of separator curves that X and Y can have in common. Now to some implementation details. We found that a simple Fiedler vector-based method to find a graph cut works quite well and gives relatively balanced components even for geometrically complex meshes. So if we have a mesh here and we apply this method, then it will find us a graph cut shown here by these dashed edges that splits the mesh into two approximately equally sized parts. And in order to then find the corresponding separator curve induced by this graph cut, we first sample all the cut edges at their midpoint, connect them, and then apply some smoothing steps to make the separator curve a bit smoother. Here's an example where we do it for the double torus. In the first step, we split the surface along this separator curve, and the next step, and then we split the blue part again into these two parts, and so forth until we arrive at the level of leaf patches. Now, once we have our bisection tree, then for every surface patch we create while building the tree, for example this one, we do the following. We first consider all the separator samples of all the separator curves that we use to split this patch into further sub-patches. And for each of these samples, we use our black box geodesic distance method to compute a distance field to all the points in this patch. So here it will be all the green and the blue vertices. Once we have this information, we loop over the vertices of the mesh, of the patch P, and for each component of the separator curve that we use to split this patch, we approximate the distances to all the samples of the component with a polynomial of low degree. And that is what we then store, or rather its coefficients, what we then store in the database. We implemented all this in MATLAB, and if we run it for the Stanford bunny with roughly 5,000 vertices using bisection until the leaf patches have 30 or less vertices and polynomials up to degree 12 as our approximating distance functions, then we get a database that is only 3 megabyte large, and the pre-processing takes 5 minutes if we use a linear method for computing the distance field from all the separator samples to the points in the corresponding patches. That means if we do it for fast marching or for DGG, or 30 minutes if we compute exact geodesic distances using VTP, which is quadratic. Now with this database we can handle several thousands distance queries per second, and the average relative error, which is of course induced by the approximation of the exact separator distance functions by polynomials, is less than 0.5%, and that's measured of course relative to the distance that we would get if we use the same black box that we used for generating the database. Okay, what have we learned today? Well, we have learned about a new way to compress geodesic distance information that works with any geodesic distance algorithm as a black box and leads to a compressed database of size mn log n, where m is just a constant and n is the number of vertices of the mesh. And this database can then be used to answer point-to-point queries in worst case m log n time, and we show that average case time is actually only O of m. And this constant m is inversely proportional to the relative error. Typically, we found that choosing m equals to 12 is a good choice, leading to an error less than or equal to 0.5%. But of course, if you increase m, you can decrease the error and vice versa. But that also has then, of course, a linear effect on the database size. Thanks for your attention.